Hi, you are at level 4 of 30 easy levels to understand everything about Einstein's theory on special relativity. Have you always been curious about what it is all about, but feared its complexity or its math? Then these levels are for you. This level we will talk about losing weight and calculus. GP, hit it! Today we are going to talk about how to lose weight fast. It will also give us a nice introduction into calculus. Calculus is a great piece of work and it's an important concept that we will need while climbing Einstein's mountain. If you're new to this, my name is Tom and I'm on a mission. My mission is to explain everything on Einstein's theory of special relativity in 30 easy levels accessible to everyone. If you want to know more about these levels, you can see my introduction at level number 1. But today we are going to lose weight. How to lose weight fast. Dear viewers, I've read many books on this topic. I dropped my weight 20 kilos several times. I don't have any issue in losing weight. My issue is keeping it at that level. But there's a lot of information out there and you can spend tons of hours and money into all kinds of experiments to lose weight, but it's really, really simple. I'm gonna put my end conclusion on how to lose weight on the board. How to lose weight fast, here we go. You drop your calorie intake, is it IY? I'm not sure. Intake below 2,000 kilocalories if you're a male, and if you're a woman it's a little bit less. This is it. I mean, you don't have to read the books anymore, you don't have to spend all these hours studying this. This is how you lose weight fast. Period. There's nothing more to it. If you want to know how to lose weight in a healthy way, that's a whole different story. I could talk about hours on that topic. If you want to know a little bit more about the role of sports, sports play a great role when it comes to health. But they're, I think, the worst strategy ever if you want to lose weight. So don't try to lose weight in the gym. You do this for something else. So there you go. An interesting fact also is this one. Kilocalories. When you go online and you look for how many calories is in something, usually they tell you calories. Well, in fact, they mean kilocalories, like 1,000 times more. So I'm not sure how this went, and how they got away with it. But, let's say I'm an employee of a fast food service and I'm delivering a cheeseburger. And then I ask a scientist how many calories are in my cheeseburger. And the scientist said, there are 300,000 calories in your hamburger. And you're like, I can't put that on the label. I'm just gonna tell my customers it's 300. And that's what they did. And they got away with it. By the way, I'm a big fan of cheeseburgers. It's my favorite fast food. So, losing weight. Enough. So, we'll continue now and have a look at calculus. Let's talk about calculus. Calculus is the mathematical study of continuous change. You could also say calculus is tricky. In fact, I think it's one of the toughest pieces on the mountain. My ambition is not to make everyone, we're not going to practice calculus a lot. my ambition is to make sure that we all are able to read calculus. It has two major branches, differential calculus and integral calculus. The first one is about stuff that changes, and the second thing is about adding stuff up, summations. That's all it's about. It was invented in the late 17th century by Newton and Leibniz. These are incredibly special people. And, well, they also used a lot of shampoo. Let me show you their picture. Here's Newton and here's Leibniz. Especially Leibniz. I mean, there's so much hair. If hair equals wisdom, I'm in trouble here. So these are our first two rock stars that we meet now on our way to the top, Newton and Leibniz. And Newton is a case. It's a special case. You know, I said we will be ranking the rock stars, and I wanted to build up from 10 to the number one spot, but Newton is here. And he's at number one. He is the greatest from a science perspective, and he's almost the greatest from a mathematical perspective. And his development of calculus is one of the reasons why he's at the third place of the greatest mathematicians ever lived, and in general, the biggest scientist ever lived. Leibniz is the third biggest scientist and is considered the 10th greatest mathematician. Although there are many lists online, I just picked one that I liked, you know, but they are in the top 10, you know, and that's where they are. The first part, derivatives. It's finding derivatives by differentiation. Right? That's part of calculus. It's still vague, right? It's abstract. And I think it's difficult, and that's why people drop math in high school and they studied something else. I have nothing against psychology or law or anything. In fact, psychology was almost my number one choice after high school. I did something else, not law, but yeah, it's difficult, and we need it. We need to get up to the mountain. So what we are going to do is we're going to stretch. You're going to breathe. Make your world small. Put your phone away, all external inputs. Focus in the here and now. And you will master this piece, I'm sure. And we will do so by continuing to talk about losing weight. So here is a table. It's a true table. It's one of my many endeavors to lose weight. And in this case, I hit the 86.2 mark, and that was for me like, I really need to lose weight now. That was at the beginning of week 1. And then I started to lose weight, and I dropped 600 grams or 0.6 kilo in the first week. So at the beginning of week 2, I was 85.6. So we had liftoff. Then I got the hang of it and I dropped a kilo. So I gave myself a treat. Well, I should have done so. So it was 0.2 kilos the next week. And then it was steady 0.5 kilos a week, which is a good pace, right? If you can keep that up in the long run, you're on track. So this was my table with my weight loss. And then I said, well, these scientists, or especially mathematicians, they often don't like tables, as we saw in the happiness formula in one of the previous levels. They like graphs. So let me put it in a graph as well. And there you go. We have the weeks, and we have my weight in kilos at the beginning and the end of each week. And this is a line, a curve that tells me what my weight is at every point in time. So here it is again. Now we can make some statements with this graph. Let's do some. Number 1. In these 5 weeks, I lost 2.8 kilos. You can do the math yourself, right? You can just subtract the weight in week 5, at the end of week 5, by the weight at the beginning of week 1, and you see there's 2.8 kilos gone. Yay! So per week, that's on average 0.56 kilos. I mean, this makes sense, right? No, it's not that difficult. So if you would have drawn that in a red line, and you would say, okay, the average is also the weight loss that happened every week, then I would have been on the red line, like a steady line. I didn't, I accelerated in losing weight in week number 2, and then I dropped, and then the curve went like this in week 3. But yeah, I could have done the red line, right? I also see in the table that after the first 3 weeks, on week number 4 and 5, I was losing 5 kilos a week, steady. So here's another graph, and I made that part of the graph red. So this red line is steady losing 0.5 kilos each week. A third statement, in week 2, I was at my best. I lost a full kilo in a single week. If only I could have held that pace. And if you draw a red line through that piece of the curve and you extend it a little bit, you see that if I stayed on that path, on the red line, I would have dropped many kilos. In week 3, a kilo, in week 4, a kilo, week 5, a kilo, and I would have lost a lot more weight than just 2.8. So this is easy, we can take the graph and do some analysis on it for different weeks. Well, that's, I think, derivatives. So let's now see, congratulations, see how the evil mathematicians, whom we've met before, turn this thing around. So here again, the graph, I put some days in there as well. The purple one is the average weight loss. The red line is the best week ever, 1 kilo a week. And the green part is the steady pace of 0.5 kilos a week. Let's see what normal people would say about this graph and how evil mathematicians will tell it to you. Number 1. The graph that I just draw shows me the kilos on the vertical axis at some time, and that's it. Now, evil mathematicians will say y is a function of x. Y represents here weight in kilos, x represents time in weeks. You have to know this. If they don't tell you this, that it's about weeks and weight and kilos, you're like, why is fx? But you need to have a little bit more background and context to understand what they're talking about. So there you go. I could also say at the end of the week 1, I weighed 85.6 kilos. Mathematicians do it like this. They put in the 1 for after week 1 in the x, and then they say the y, the weight in kilos, is 85.6. There it is. Now it gets more tricky. I lost on average, remember we did this, 0.56 kilos a week. Well, mathematicians will tell you this. Symbols, Greek symbols, triangles, y's and x's, and they get to the same conclusion. Well, they say it's minus 0.56 because I'm talking about weight loss and they are talking about weight. And the weight changed minus 0.56 kilos between the beginning of week 1 and the end of week 5. I'm going to explain a little bit more about these symbols later. The delta, the triangle is the D for delta, the difference. So you want to know the difference of the weight per the difference in time. X was time, remember? Y was weight. So there you see, if you take the weight at week number 5, 83.4, minus the beginning, and you divide it by the total difference, delta in x, delta in weeks, which is 5 weeks, then you get to the same number. So that's what they use. They use these symbols, and we need to feel familiar with them. That whenever we see deltas, we know it's about change, stuff changing. That's all you have to remember. Another one, in week 4 and 5, I kept losing 0.5 kilos each week. I think I made a typo there again with the double O. Apologies. So sometimes they say, well, let's not use the delta, Greek delta, the triangle, but let's use the D for difference. And basically they're saying, you know, the rate of changing my weight at the beginning of week 3, which is in beginning of week number 4, which is the end of week 3, is the same as the end of week 4, same as the end of week 5, and it's half a kilo every week. So when you see these, also think, calculus, differences, deltas. Then I said, and week 2 I dropped 1 kilo each week, and I wished I could have followed that line. Oh, goes too fast. Sometimes they don't use the D's. You know they're evil, right? I told you many times, and in level 1 I even told you why they are evil. Sometimes they use this accent. Y accent. Sometimes they use it on the Y. Sometimes they use it on the F for function. It's just weird. All we have to remember, if we see this accent, think about differences. Calculus, differences. So let's do an overview and some abstraction. The derivative is the change of something, stuff A, when stuff B changes. And we need to be careful with the units here. Here are some examples. The derivative weight loss per day, in this case, stuff A is the weight in kilos, and stuff B is the time in days. So it is how much does the weight in kilos change when time in days changes. And if you know this, then you have the derivative, the time derivative of weight. And we call this weight loss. Let's look at temperature. Coffee is cooling down. So the temperature is changing while time just ticks on. So time is changing as well. If you know how much the temperature drops each second, each minute, each hour, you have the time derivative of the temperature of the coffee. Another example. I am somewhere. Well, a car is somewhere at a location. But the car isn't staying at that location. It changes location when time just ticks on. An hour later, he's somewhere else. Let's say 100 kilometers down the road. So we could say you changed your location 100 kilometers in 1 hour. So your time derivative of location is 100 kilometers each hour. And we have a name for it, and we call this speed. Velocity. Velocity, speed, is the change of location divided by the change in time. We actually say it literally, 80 miles per hour, 100 kilometers per hour. Speed velocity is a derivative, probably the most intuitive one we all know. You could also look at stairs. I'm walking the stairs. Each step changes my height above the ground, so you could say the step derivative of height is something like walking the stairs. And we talked about weight loss again, but now not from a point of view in when time changes. No, let's see how my weight changes when I do exercises. And you could say that's the exercise derivative of weight. And as I said, it's a very bad strategy to use exercises when losing weight. Well, no, it's very good to do exercises for a million reasons, but losing weight is just not one of those million. So, abstract the stuff B derivative of stuff A. That's how we say this. And this is how we use it in notations. The stuff B derivative of stuff A is either the delta, the change of A, divided by the change, the delta of stuff B. When they use these triangles, you usually have big deltas. It's like averages. Like we said, in 5 weeks, the change in weight was 2.8 kilos. The change in time was 5 weeks. So 2.8 divided by 5 is 0.56 kilos per week. That was the time derivative, the week derivative of my weight in kilos. If you make the difference smaller, you not look at how many kilos did you lose each week, but each day, or even each minute, or each second, or each microsecond, then mathematicians drop the delta sign and they replace it with a D. So when you see the D for difference, still it's exactly the same as the delta, only a very, very small delta, divided again by a very, very small delta of stuff B. The ratio might not be small, but both of them might be very small. And then there's this evilness that they use a different D, like a D like this. You know, it's like the small Greek letter delta, I guess. It's not something we will use up on the mountain, I think. Well, maybe we will do, but let me try to explain. Let's look at weight loss. We all agree that if you reduce your intake in food, your weight will drop. And we also agree that if you would exercise an enormous amount of exercises, that you will lose weight from those exercises as well. So losing weight is depending on 2 variables, well, many, but in this case 2. Your calorie intake and the number of exercises done. So if A is your weight, then the difference of your weight could change when you change your intake, but it could also change when you change the number of exercises done. So there are multiple B's. So if you see the Greek delta, they call it partial derivative. And why? Because you're looking at the change of A when stuff B changes. But stuff A might also change if something else, stuff C, changes. And the Greek small delta gives you a hint that you know, A is probably depending on more than just B. And that's it, you know. Let's not make it any more difficult than it is. A special derivative is when you say, I want to look at how stuff changes when time changes. Those are called the time derivatives, and we use them a lot in physics. So if you want to do delta, that was like the car, you know, the car moved its location. The delta of location was 100 kilometers an hour. In delta t, 1 hour, so the average velocity or speed of the car was 100 kilometers per hour. It could have been that during his this hour he drove faster or slower, but on average, you know, and that's why we use the deltas, on average it was 100 kilometers every hour. If I wanted to know how fast was this guy or girl going, after 23 minutes, 32 seconds and 5 milliseconds, maybe he or she was going like 130 miles per hour or kilometers an hour. So then I would use the delta. And well, in this metaphor there's no partial, but if it's partial then it's the delta. And then now more evilness comes in. Because we use the time derivatives so many times in physics, they gave it their own symbols. Sometimes they put a dot on top of stuff A. And that's a time derivative. You have to know. That's a secret arrangement they made. And then they sometimes do something different. They do the accent. We saw the accent already in the previous slide. The accent is particularly evil, and I will tell you why. If you go online and search for Einstein's theory on special relativity, you will probably end up looking at a set of equations called the Lorentz transformation. We will talk about Lorentz and its transformations in depth. We will do everything. We will do everything from scratch. And in those equations, they use an accent. But it has nothing, and I mean nothing, to do with time derivatives. And that's why mathematicians are evil. They are just playing with our souls, introducing symbols, mixing them, and depending on the context, they have totally different meanings. It's evil. Let's look at calculus. Calculus is also the second part, and it's not about how stuff changes when other stuff changes. It's more about adding stuff. It ruined math as well, because it's tricky, but again, stretch, breathe, make your world small. We can do this. Yes, we can. So here is my graph again of weight at the end of each week. I could draw a different graph with almost the same information. Are you ready? Just look at it for a few seconds. So during week 1 we lost 0.6 kilos that week. You see that in the right graph. In the second week we lost a full kilo. In the third week 0.2, and after week 3 and 4 we did 0.5. So there you go. If I would have given you the left function, the left graph, you could have drawn the right one, right? You just would have said, oh, you know, week 1, 0.6, so I put in 0.6. Week number 2, 1, I put 1. So you can derive the second graph from the first one. It's easy. You can do this also the other way around, almost. You don't know the starting point. You don't know how much my weight was when I started losing weight. But if I tell you, Tom, you started at 86.2, then I have all the information in the right graph to draw the left graph. If you want to know, I mean, just pause it and try to see if you can do it. But if you know it's 86.2 and you know I drop 0.6 in week number 1, you probably do 86.2 minus those 0.6 is 85.6, and you draw the second point in the graph. So these two graphs are almost equivalent. The left graph is more about differentials, which is a big part of calculus we just talked about. The right piece is more about the integrals, the other piece of calculus, adding stuff up. And let me show you a little bit more on this. So here we have the same graphs again. Let's look at the left graph. If you would take the difference between the weight at the beginning of week 1, the end of week 0, and the end of week 5, we get 2.8, right? We've done this. But you can get this 2.8 from the right graph as well, in a different way. Here's how. You add up the surface area below the graph. If you do this, you also end up with 2.8 kilos. So it has the same information. It looks really different, but it's the same information. They look a little bit like fat cells, right? I think they're water drops, the texture that I used, but let's say they're evil fat cells. Go away. Now let's introduce more symbols. We saw deltas and d's when we dealt with differences. When we deal with summations, like summing the areas below the right graph, they introduce the integral sign. It's like this. That's the one. So whenever you see this, you only have to remember they are adding stuff. We're doing calculus and they are adding stuff together. And in this case we could say the weight, which is a function of time, equals 86.2, my start weight, minus the area below the right graph. The right graph is g, is the function g, and it's a function of time. It's the weight loss per week for a given time in weeks. And if I would add those up between 0 and point t of interest, could be 1, could be 2, could be 5, could be anything, then I get my weight loss. So the weight loss per week, I called it WLPW, is a function of time as well. I called that function g. I could have called it anything, you know, h, b, whatever. I called it g. It's the derivative, that's what we saw in the first part, of function f, which is on the left. The time derivative of function f on the left is well, it's a time derivative, you know, what can I say? And if you have the time derivative of a function and you add the surface areas below that function, you get the original f, if you know the starting point. I know this is a lot to take in. And just don't worry. Keep your world small. Keep breathing. So total weight loss on the left is easy. Subtracting two numbers, minus 2.8. Weight loss using the graph on the right is a little bit more difficult. It's well, you just do you remember substitute and shovel in level number 2? We are substituting here. We're substituting f in t is 5 with the equation on top, and then we say minus f for t is 0, and then you get minus t integral, adding stuff up between t is 0 weeks and t is 5 weeks, of function g on the right, which is the time derivative. Well, I do understand this is a lot to take in, but in summary, d's and deltas, stuff changes. Integrals, we're adding stuff up. And they're like two sides of the same coin. And sometimes it's really convenient to use this side of the coin, and sometimes it's really convenient to use the other side of the coin. Congratulations! If you are still breathing and here, you've made it all the way through the end of this level. Really, congratulations. Thank you for watching, and I hope to see you at the next level. GP, hit it!